Hello. In the previous lecture, we have seen that in a Housdorff space, any compact subset and a point which is not in that compact subset can be separated by two disjoint open sets. Here. So now, in the next theorem, we will prove a very important property of Housdorff space. We will show that every compact subset of Housdorff space is closed. So that's this theorem. Every compact subset of Housdorff space is closed. So let X be any compact subset, or be any Housdorff space, and C be any compact subset of X. We show that C is closed, and we know that in topological space a set is closed if its complement is open. So to prove C is closed, we show that its complement is open. If C complements phi set, is the phi set, then there is nothing to prove. So assume that C complement is not phi, and let's choose any point X in C complement. Then X is not in C. Now by this theorem, by previous theorem, if X is not in C, then we can separate X and C. Then by previous theorem, we can separate X and C by disjoint open sets, say U and V. So that is X belongs to U and C is subset of V, and they are disjoint. So it's like this. This your Housdorff space X, and that's a compact set C, and that's a point X, okay, which is not in C. Then we have two open sets U and V which are disjoint. U contains the point X and V contains the compact set C. V contains the compact set C. So this C is a subset of V. C is subset of V, where X is not in where X is not in C. Where X is not in C. So from this you can see that that's your U. You can see that C complement, which is this whole set C complement. That's C complement. Okay, this is C complement. This shaded region, it's a C complement, and you can see that U is subset of C complement and X belongs to U. So therefore X belongs to U and U is subset of C complement. U is subset of C complement. So thus every point of C complement is its interior point. Thus every point of C complement is its interior point. Is its interior point. So therefore C complement is open and hence C is closed, and hence C is closed. That proves this theorem completely. So we have proved that in Housdorff space, every compact subset is closed. So now in the next theorem we will show that a bijective continuous mapping between Housdorff space and compact space, between compact and Housdorff space, is always homeomorphism. That's the next theorem. So first we define homeomorphism. Let me define first homeomorphism. Let X and Y be two topological spaces. A mapping f from x to y is said to be homeomorphism if f is bijective, continuous and open mapping. So continuous means inverse image of open sets open, and open means image of open sets open. If U is open set in X, then its image must be open in Y. Then we see those mappings are open mappings. So if a map is bijective, it's continuous and open, then we call this map a homeomorphism. So next we have following fact which we'll use in the theorem. That's a mapping. You can easily do this. A mapping F between the topological space X and Y, where X and Y topological space, is open if and only if it is closed. A mapping F maps open sets onto open sets if and only if it maps closed sets onto closed sets. That's very simple fact that you will do yourself. Now we prove our main theorem. A bijective continuous mapping, f x to y between the topological spaces X and Y, between the compact space and Housdorff space. Between the compact space and Housdorff space. Between the compact space, X is compact space, and between the compact space X and Housdorff space Y. And Housdorff space Y is homeomorphism. It's bijective, it's also continuous, but we show that it's homeomorphism. That means we show that it's also an open mapping. So for open mapping, it's sufficient to show that it's an for a homeomorphism, it's sufficient to show that it is an open mapping. So to prove F is homeomorphism, it is sufficient to show that F is an open mapping. Because the other property is that bijective continuous, it already has those properties, bijective and continuous. So we need just to show that this F is an open mapping. And by this fact, F is open if and only if it's closed. By above fact, we show that F is closed mapping. So closed means we show that it maps closed sets onto closed sets. Take any closed set in X, we show that the image of the closed set is closed in Y. It maps closed sets onto closed sets. So let's take any closed set. Let F be any closed set in X. So we show that image of F under the map F. we show that f of f is closed in Y. However, since f is closed in X and X is compact, and it's a well-known fact that the compact subset, the closed subset of compact sets compact. Closed subset of compact sets compact. It's a well-known fact. F is a closed subset of X and X is compact. Therefore, F is compact. Therefore, F is compact. Since X is compact, and F is closed subset of X, therefore F is compact. And we know that continuous mappings maps compact sets onto compact sets. Therefore F is compact, and therefore F is compact. Now again, since F is continuous, so therefore f of f, image of f under F, image of a compact set under continuous mapping F, is also compact subset of Y. Is a compact subset of Y. Now here, F is a mapping between compact space and Housdorff space. So Y is Housdorff space, and f of f is compact subset of Housdorff space. We already have proved that this result. Every compact subset of Housdorff space is closed, and f of f is a compact subset of Housdorff space Y. Therefore, f of f is closed subset of Y, because every compact subset of Housdorff space is closed. So thus by previous theorem, f of f is closed subset of Y. So hence f is a closed mapping. It's a closed mapping because it maps closed sets onto closed set. We have taken f to be closed we have taken this f closed subset of X, and we have shown that its image under F is a closed subset of Y. Therefore, F is a closed mapping as required. So this proves the theorem completely. So in particular, it shows that this let's example here. We know that the compact subsets of real line are precisely closed and bounded sets. So if f from A to B to a set of real numbers, and we know that it's a matrix space, and every matrix space is Housdorff space, and this one is a compact subset of R. So it's a mapping between compact set and Housdorff space. So if it is bijective and continuous, is bijective and continuous, then F is an open mapping. F is an open mapping. So if this map is bijective and continuous, then by previous theorem it maps open sets onto open sets, closed sets onto closed sets. So that's the application of this theorem. Now next we define when 2 points are separated by some map. So next the next definition let X be a topological space. Let X be a topological space, and x and y, they are points of x such that x not equal to y. They are two distinct points of a topological space X. If there exists a continuous map from X to R such that there exists a continuous map f from X to R such that fx is not equal to fy, then we say x and y are separated by the continuous map f. If there exists a continuous map if there is a continuous map f from X to R, or we can say if there exists f belongs to CXR. CXR denotes a set of continuous mapping between X and R. So if X is a topological space and X and Y are two distinct points of X, and if there exists a continuous map from X to R, or we can say a map f belongs to CXR such that f of x is not equal to f of y. F of x is not equal to f of y. Then we say f separates the points. This f, it separates the points x and y. F separates the points x and y, or we can say set up continuous mappings from X to R. CXR separates the points x and y. It's equivalent. We say f separates the points x and y, or equivalently we say CXR, it separates the points x and y. It separates the points x and y. The next theorem is the connection between the points between the topological space in which CXR separates the points of that topological space and the Housdorff space. This property is very important. It's the connection between these two, Housdorff space and the separation of points of a topological space by means of these the set of continuous mappings. So, and the theorem is the following. It states that if we have a topological space X, and if any two points of X are separated by CXR, then X is Housdorff. It's T2 space. If X is a topological space and any two distinct points of X are separated by CXR. CXR means the set of all continuous mappings between X and R. And any two points of X are separated by CXR, then X is Housdorff space. The proof is very simple. So let's prove this. It's Housdorff space. For Housdorff space, we need to show that any two distinct points of X can be separated by disjoint open sets. So let's choose any two points. Let X, y belongs to X such that X is not equal to Y. Okay. Now, since CXR separates the points of X, distinct points of X, therefore it will separate these 2 points also, because they are distinct points of X. So then there exists some continuous map in CXR such that f of x is not equal to f of y. F of x is not equal to f of y. Now assume it's since fx and fy, they are real numbers because f is a mapping between x and r, so that means f of x is a real number, f of y is a real number. So let's assume that fx is less than fy. So we can assume this, or it may be greater. So let's take this assumption, fx less than fy, and choose any point between fx and fy because the r is dense in itself. And choose we can choose the arithmetic mean of these 2 points also, which lies between these 2 points fx and fy. So let's choose, and choose r belongs to r such that fx less than r less than fy. Now we define sets. We define 2 sets here. Let's define A. Let A, it's a subset of x. It's a subset of x. Z belongs to x such that fx fz less than r, such that fz less than r, and B is equal to those points of x such that fz greater than r, f of z greater than r. So clearly these 2 sets are non-empty because we have fx such that this fx is less than r. So that means x belongs to A because x possesses this property. F of x is any point in x satisfying this property is the point of A, and x has this property, f of x is less than r, therefore x is the point of A. Similarly, f of y is greater than r, and any such point belongs to B, so that means y belongs to B. Y belongs to B. So it means that A and B are disjoint subsets of x. 1.7. So then x belongs to A as f of x is less than r, and y belongs to B as f of y is greater than r. F of y is greater than r. So therefore A and B are non-empty sets. Now we